So, section 15.5, directional derivative and the gradient. Oh, we're going to go back to vectors. Remember we talked about that we were going to forget about vectors for a while? They're coming back. So now here's where we're going to put vector value functions with multivariable functions to find another kind of derivative. It's not a new rule. It's not a new differentiation rule. It's just a different way to take a derivative, which is the directional derivative. Okay. So in the previous couple of sections, we were finding partial derivatives. That is for the most general, for the simplest case of it, for a function of two variables, all right? Because for three or more variables, geometrically doesn't give us any visual here. All right. So number one, what are we going to do? Find and use directional derivatives of functions of 2 and 3 variables. Define what the gradient is, and then extend all this to 3 variables and look at applications. So here's the thing: a diagram. So, for this diagram, suppose you have this surface. That's going to be a bit hard to plot. Okay, yeah, this is the surface with maybe. All right, that's a surface. And let that be a point on the surface. Again, from section 15.3, where we learn about partial differentiation, again, it's the same concept as back in Calculus 1. That is the slope at a given point, but not for a curve this time. This time is on a surface, but because we have more than one variable, so if we took the derivative with respect x, that gave us the slope in the x direction. That is, notice how I'm trying my best here to draw a line that is parallel to the x-axis. So that is partial of f with respect x, where this is on surface f. Likewise, okay, this slope right here, this line, this tangent line, will have a slope given by partial of f, but with respect to y, and that's going to give us the slope of the tangent line on the surface, not the curve, on the surface, parallel to the y-axis. That is the rate of change with respect to y, the rate versus the rate of change between f and x. All right. But again, we also kind of discussed that the world we live in is it's not a rectangular world, right? Yes, I know we use maps and Cartesian planes to describe locations as order pairs, as points on the Cartesian plane. So of course, if we move in the x direction or in the y direction, but what if I want to move in a different direction? What if I want to move from this point, say, from this point, not along the x-axis or around the y-axis, but in this direction, maybe, say, 30 degrees, right? 30 degrees. And this is what you guys do when you go hiking, and when you're simply walking, you want to find a way around a hill or something. Well, you're not just going straight and then like this and then like that, forming 90 degrees for every turn. No, you can turn basically in your favorite direction. So we need a new way to differentiate this function to give us such slope, because if we move in this direction, for instance, or in that other direction, which is no longer in the x direction or the y direction, that means what are we doing? We are twisting that tangent line, right? And to twist that tangent line, what do we need? We need a steering factor, so to speak. What is that steering factor? It's in the form, because it's going to create rotation. Guess what? How do we get rotation? Isn't that just a vector that contains cosines and sines? Circle, right? look at the expression for the directional derivative. That means the new slope right here. Let me call this part. Oh, let me call this d u of some f of x y. So that means the factor. Okay, so we need to find the two derivatives: the derivative with respect x and the derivative with respect y. To look at the rates of change in the x direction and the y direction. But to go in a different direction, we need, again, what we call a steering factor. That is, multiply the rate of change with respect x by the cosine, because, surprise, x equals cosine, and the derivative with respect y by sine, because, surprise, y represents the sine function, right? So that's the steering factor to come up with the derivative in any direction, in your favorite direction, other than just x and y. All right. So now, for instance, let's say you are at a point on the surface, and instead of going along the x-axis, along the y-axis, no, I would like to go in the direction of, say, 60 degrees or 5 degrees, 17 degrees. All we're going to do is find the partial derivatives, evaluate it at the given point, and multiply the x derivative by the cosine of the angle and the y derivative by the sine of the angle. Let's have a look at one example to illustrate this idea. Okay. So given the equation of the surface z equals to x squared plus 3y squared minus 5, I can tell this is an elliptic paraboloid because both variables are squared and the coefficients are different. So that's going to make it an elliptic paraboloid, and it's shifted along the z-axis down 5 units. Find the directional derivative of f at the point 1, 3 in the direction of this vector. That is, I would like to move from that point on the surface to, what is that, 30 degrees. Not anymore in the x direction, not anymore in the y direction. I want to know what's my derivative, what's my rate of change if I go 30 degrees along that point. All right. So let's describe this as a vector, and let's call this u. Okay. Which is, by the way, it's a unit vector. So a better way to explain this directional derivative. So again, we're no longer finding the rate of change in the x direction or the y direction, but this time we're finding the rate of change in the direction of a vector. So here's where we put back vectors into our calculations. Okay, so we have this. Let's find the partial derivative of f with respect x, which is 2x, the partial derivative of f with respect y, that is 6y. And I believe we have everything we need pretty much. All right? So, this symbol right here, d subscript u of f of x, denotes the derivative of the directional derivative of the function f in the direction of the vector u, which has to be a unit vector. And well, in this case, we're given a unit vector. Do you see the coefficients of cosine and sine are 1? There's other cases that we will discuss soon. Okay, so let's denote the directional derivative of u. Don't forget to put the arrow because it's now a vector. Notice it's bold case on the notes. F of x, that is partial of f with respect x, cosine of the angle, plus partial of f with respect y, sine of the angle. But we already found those values, right? So that is number 1, partial with respect x, that equals to 2x times cosine of the angle, which is 5/6, that is root of 3 over 2, plus 6y times 1/2. Let's reduce this expression to lowest terms. That is x root of 3. I'm going to write the root of 3 after the letter x, because if I write it the other order, it's easy for us to think that the x is inside of the radical, which is not the case. Then 6 over 2, that equals to 3y. So now that means we have an expression to find the derivative at every single point on the surface, as long as from any of those points we move 30 degrees. For 45 degrees, well, then I would have to compute this cosine and sine. For 135 degrees, I would have to compute those cosine and sine again. All right? So, the directional derivative of f in the direction of the vector u at the point 1, 3, that equals 6 times y, careful, 6 times 3 plus x, no, 6 times 3, no, what am I doing? Okay, x, which is 1 times root of 3 plus 3 times y, which is 3 times 3. That is root of 3 plus 9. So that is the value of the slope on the surface at the point 1, 3 if I go in the direction of 30 degrees. Alright guys.